So this is February March 22 P42 question 1, and as you can see, the first part is asking us to represent gravitational field around P, and P is a point mass. So we know we simply have to draw lines and show arrows moving towards P, right? So that is what I'm trying to draw here, though it's not a good drawing, but that's the idea. And we know that the gravitational field is going to act in concentric circles. We don't have to draw these circles. I'm just showing you that as we're going to go far from this point, the gravitational field is going to get weaker, right? Then for part B, we have a moon is in circular orbit around a planet. Explain why the path of the moon is circular. Okay, so basically so because it's circular motion, you know what type of force is involved: centripetal force. Next thing you need to think about is what's providing the centripetal force. So in this case, it's going to be the gravitational force between the moon and the planet. So that's what I need to write about, that first of all, gravitational force is providing centripetal force, and that when a centripetal force is going to act on the moon, it's going to undergo centripetal acceleration, in which the force is perpendicular to its velocity. So that's what I need to write about in this part. Okay, so for the next part, we have a graph of r cube on y-axis and 1 upon omega square on our x-axis, and then they're telling us that basically they have given us the equation and we need to prove this equation, right? So we know that if we talk about the gradient, it should be it's rise upon run, right? So it's going to be r cube upon 1 upon omega square, and that means that r cube omega square, wherever we see that, we're gonna put that equal to gradient. So first of all, I'm gonna start with the simple equation that gravitational force, it's gonna provide the centripetal force, and then whenever I'm going to see r cube omega square, I'm gonna replace it with gradient, right? So that's the motto in mind, and I'm gonna start doing it. One thing to notice here is that I could have used the equation mv square upon r, but here I used mr omega square for centripetal force, and that is because I kept the gradient in mind, right? Okay, so for the next part, I need to calculate the mass. So for that, I will have to first calculate the gradient. Now gradient, is gonna be change in y upon change in x. I will need the values of 2 points, coordinates of 2 points, and then I will simply put it in the equation m equal to y2 minus y1 upon x2 minus x1. I will just consider any one coordinate as x1 y1 and any other coordinate as x2 y2, and then I'm gonna substitute the values in the equation, right? So that's what I am doing right now. Alright, so now I'm just gonna substitute the values in. I know that g is a constant. It's going to have a value of 6.67 into 10 to the power minus 11. And we have our gradient as 7 into exponent 15. Okay, then we have determined the speed of a moon in orbit around the planet with an orbital radius of 1.2 into exponent 8 meters. Okay, so this time I want the velocity, right? So I'm gonna keep my gravitational force equal to mv square upon r, right? So gmm upon r square equal to mv square upon r, and I'm gonna derive a formula for my velocity and then simply substitute in the values. Keep in mind, however, one thing, that the mass of the moon is cut off. What we're using here is mass of the planet, because when we have written the formula for centripetal force, that includes the mass of moon, right? But when we're gonna cross it out, then the mass of planet is left, not the moon.